Before the age of computers, the world moved at a much slower pace. Calculations that now take a fraction of a second could consume a lifetime. Imagine trying to predict the weather. Imagine trying to design an airplane. Imagine trying to understand the secrets of the atom using only a pencil, paper, and the human mind. The most complex problems were simply out of reach, locked away behind a wall of impossibly large numbers. Human calculators, rooms full of people with adding machines, were the fastest processors on the planet. They worked for days, weeks, and months. They worked to solve equations that a simple laptop now handles before you can blink. It was a world constrained by the limits of human calculation. This was a time of immense curiosity and urgent need. Scientists and engineers dreamed of a machine that could think with numbers. They dreamed of a device that could perform these monumental tasks automatically. They weren't just thinking about convenience, they were thinking about necessity. During World War II, the need for faster calculations became a matter of national security. Firing tables for artillery, for example, required complex ballistic trajectory calculations. Each new weapon needed its own set of tables, and producing them by hand was a slow, painstaking process. This pressing demand for speed set the stage for a revolution, a spark that would ignite the digital age and change our relationship with information. The dream was simple, yet profound. Could we build an electronic brain? A machine that could take instructions and execute them at speeds no human could ever match. This wasn't just about building a better calculator, it was about creating a tool to extend the human intellect itself. The universe of computation was about to be born. And then, it arrived. In 1946, the world met ENIAC, the electronic numerical integrator and computer. It was a monster, a behemoth, not a desktop, a room-sized machine. Spanning over 1,800 square feet, weighing nearly 30 tons, imagine 40 massive black metal cabinets filling a room, all tied together by a dizzying web of thick cables, 18,000 delicate vacuum tubes, 70,000 resistors, 10,000 capacitors, a landmark, a testament to human ingenuity. What made it special? Speed. Unprecedented, mind-bending speed. About 5,000 additions per second. In the 1940s, miraculous. A calculation that took a human 20 hours could be done in 30 seconds, like trading a horse-drawn cart for a rocket ship. A tool that could outcalculate the human brain at scale, built to compute artillery firing tables for the US Army. Its creators knew it could do much more. A general-purpose computer. But power came with challenges. A team of operators, mostly women, had to rewire it by hand. Still, ENIAC proved large-scale electronic computation was possible. After ENIAC lit the way, the race was on to build smaller, faster, and more reliable machines. The first major leap forward came with UNIVAC-1, the Universal Automatic Computer. Delivered in 1951, it was the first commercial computer produced in the United States. Unlike ENIAC, which was a one-of-a-kind research project, UNIVAC was designed for business data processing, government data processing. It famously, and correctly, predicted the landslide victory of Dwight D. Eisenhower in the 1952 presidential election, bringing the power of computing directly into the public eye. It was still a giant, but it was a more refined, more practical giant. UNIVAC introduced a crucial innovation: magnetic tape. While ENIAC used cumbersome punch cards, UNIVAC could read data on reels of metallic tape and write data on reels of metallic tape. This was a massive improvement. At the same time, the corporate giant IBM entered the fray. Seeing the potential of these new machines, IBM launched its own series of computers like the IBM 701. The competition between companies like UNIVAC and IBM fueled rapid innovation, pushing computers to become more powerful and accessible. As mainframes became common, one man looked at them and thought, "We can do better. We can go faster." That man was Seymour Cray. An electrical engineer from rural Wisconsin, Cray was a true original, a lone wolf with a singular vision. He wasn't interested in building computers for payroll or accounting. He was obsessed with one thing: building the fastest machines in the world. He wanted to build computers for the scientists and engineers tackling the biggest problems: weather prediction, nuclear simulations, aerodynamic design. For Cray, computing wasn't about data processing, it was about raw, unadulterated speed. Cray's philosophy was radical. While companies like IBM were building complex, general-purpose machines, Cray believed in simplicity and elegance. He famously said, "The trouble with programmers is that you can never tell what a programmer is doing until it's too late." He designed his computers with a minimalist approach. In 1972, he founded his own company, Cray Research, with the sole purpose of building the world's first supercomputer. This term was coined specifically to describe the kind of machine he envisioned, a computer so powerful it existed in a class of its own. The culmination of Seymour Cray's vision was the Cray 1, released in 1976. It was unlike any computer ever seen before. It was a sleek C-shaped tower, small enough to stand in the corner of a room surrounded by a cushioned bench. The unique circular shape was a direct result of Cray's obsession with speed. By arranging the circuit boards in a cylinder, he ensured that the wires connecting them were as short as possible, minimizing signal delays, and allowing the machine to run at a blistering 80 MHz. It was the first commercially successful computer to use vector processing, a technique that allowed it to perform the same operation on a large set of data all at once. The Cray 1 became the essential tool for anyone who needed to simulate reality, crashing a virtual car modeling a supernova. Today, the spirit of ENIAC and the Cray 1 lives on in the supercomputers that power our modern world. These machines, now millions of times more powerful, are direct descendants of those early pioneers. They help us design new medicines, search for sources of renewable energy, create more efficient cars and planes, probe the mysteries of the universe by simulating the Big Bang. The journey from a room-sized collection of vacuum tubes to the sleek, liquid-cooled behemoths of today is a story of human curiosity and our relentless drive to build better tools. It's a journey that has changed the world, and it's far from over.